magnets, etc. These all have local order parameters. Could be the pairing field superconductor, superfluid, spontaneous symmetry breaking. But there are topological phases which are beyond the standard Landau paradigm, which has no local order, no symmetry breaking. These are quantum Hall transition, and it's an example of them, but there are many other cases that people have been studying. So therefore, in this case, you need to characterize the global property, the topology. You need to figure out it has one hole or two holes, for example. A topological quantum number, which is an integer of local geometrical quantities, would be the Berry curvature, over the entire first Brillouin zone. So you need to integrate it. So we like to focus not on the standard ones, but on the topological ones, which are trickier to handle because there is no local order parameter, no symmetry breaking, so they are trickier. So the way to do it, there is here a more of a physics approach for the block states and the geometric approach. So you take the Schrödinger equation in momentum space. And you solve the question, you get the wave functions here in momentum space. So then you get the gradient in momentum, all the wave function momentum space, and the brush. So you get the expectation value here, and this is the vector potential. So indicate you get the wave function, the gradient, expectation value, vector potential, and then from here you get the curl, and you get the emerging magnetic field from this wave function. The geometric terminology, these are called like fiber bundles, this is a Berry connection, Berry curvature, but in physics it's a wave function, vector potential, magnetic field. It's the same thing. So therefore, now you need to go from geometry to topology, and there is something called the Gauss-Bonnet theorem that relates the integral of the Gauss curvature, which is K, of a closed surface with the Euler character, which is in terms of the genus here. So here it is. So therefore, the Gauss curvature is here, the Euler character is here, the genus, so is the number of holes. If it is a sphere, 0, a torus, 1. If it is a coffee cup with a handle, is also 1, etc. But then you need to compute the Chern number, which is gives you the topological character. So you take the Berry curvature, which is, again, wave function, take the gradient, expectation value, take the curl, and then you get the B. And then you integrate this in K-space on the Brillouin zone, and you get the topological number. So this can be seen as the winding or wrapping number of the map from the Brillouin zone to the state space. This became important after the pioneering paper by Thouless et al. But Thouless has several papers on this, and also Haldane and other people, and it became a big thing in the past 2 or 3 decades. Is the Chern number is the quantized number in the Hall conductance here, and appears in other problems also. So this is the quantized Hall conductance, and it has a topological origin that dates back to 1982, but has been studied for many, many years. A more recent review is this Hassan and Kane, topological insulator 2010, but there are other reviews also. So therefore, the question is how to do unsupervised learning of these topological quantum phase transitions. So we would like to identify this topological cluster. So we need to look in phase space, in feature space, they call it here, and then have the right metric and be able to find separate clusters and boundaries for a given set of Hamiltonian or wave functions. So machine learning is enriching the toolbox for studying topological quantum phase transitions. You need to have a similarity or kernel matrix to decide what's similar to what is related to. But the typical one is you take the square distance between 2 sample vectors. There is some resolution parameters. This is what we call the Euclidean metric, the standard way to measure distances. But in feature space, if you use different metrics, you can separate the clusters better. There is something called the Chebyshev metric, which is actually for this one here. We tried that. This one is, in general, you have P equal 2 is the standard Euclidean distance, and P equal to infinity, you take the largest value, gives you the Chebyshev distance, and then It's also called the L infinite norm in mathematics. But essentially, you look at the maximum value within those coordinates zk. And then for several Hamiltonian, we found that this one here is very effective, actually. So therefore, there are, exactly, so therefore the similarity matrix tells you what's related to what. You want to have a connectivity. Exactly, there is no local order parameter, and then we like to identify them, and then, so we retrieve topological transition in momentum and real space, on both spaces, using different metrics. What we found is that this Chebyshev, after trying different one, because this is part of machine learning, you need to try A, B, C, and D, and then you fail, until finally something works. Because it's an iterative process. It's not like you take the initial conditions, put them in the Maxwell equation, and get the result of Schrodinger. No. You need to try many things. And then, in this case, it sharpens the characteristic feature of the phase transitions in momentum space, while the widely used Euclidean distance is suboptimal. It's a bit blurred. It's not very good. Then we use something called diffusion map or isometric map, can be applied to implement dimensionality reduction. Has to do with this embedding we saw before. We put here the green, the yellow, and the blue. And to learn about the topological phase transitions in an unsupervised manner. The technical term is diffusion map, isometric map. Okay, so we apply this to the Su-Schrieffer-Heeger model, the Key-Wizan model, the Quench Su-Schrieffer-Heeger model, and other models afterwards. Also, we did the momentum space, real space, where the topological invariance could be unknown or hard to compute. This is an example here. This is the QWZ model, which is very popular among many theories here. There is a Hamiltonian here of this form, as a chemical potential here. There is some hopping integral here in momentum space, and then there's a Chern numbers that you can be computed in terms of these D vectors here. You take this quantity, integrate over the Brillouin zone, and you can get a topological number. And there's a way to map the 2D torus into the 2D unit sphere. And these topological Chern numbers measures how many times the mapping wraps over the unit sphere. So therefore, and then, okay, so therefore, okay, this is more technical. And then, essentially, what we did is that with this Euclidean distance, it was smearing out the topological features. With the Chebyshev distance, we're able to highlight the field. We're sharpening the clusters, the boundaries, making them much easier to be retrieved by unsupervised learning. So that's the point. Like in this case, for instance, there are many, this is a long paper that many people are liking it, essentially. There are similarity matrices for the block vector sample for this model with the Chebyshev and the Euclidean distance. In this case, the clusters are clearly separated for different phase boundaries. In the other case, a bit smeared out, so you cannot do clustering, and therefore the machine learning algorithm fails for this Euclidean distance, but it works for this Chebyshev distance because the metric is more suitable. And you can change the chemical potential as a function of the hopping integral and look at the topological Chern numbers, either analytical results or numerical results, or the ones of machine learning. There's a perfect agreement. It works really, really well. And when you look at the low-dimensional embedded images in the lattice space where you're trying to separate them, the projections are very clearly separated for different values of the chemical potential, either negative or large, or in terms of the hopping integrals. So each dot represents a cluster of hundreds of block vectors that belong to each topological phase. So it looks like few points, but essentially there are hundreds of data points clustered here on top because the separation is very nicely done. If you do principal component analysis of this model, it just fails. It doesn't do a good job. And then the clustering is kind of messed up. It is not well-spaced projection. There are poor clustering capabilities, so therefore, the principal component analysis we try other things, simply nothing was working until we found that the right way to do it. on the Su-Schrieffer-Higger model, which is very popular to study topological phase transition. There is some kinetic energy